Good afternoon, all. I've just built this. It's a whole load of opto-isolators and green LEDs and red LEDs, and there's a resistor linking each pair of optos to the next pair, so they're in a long line, a sort of daisy chain. Oh, there are also some capacitors in there as well. It's beautifully symmetrical, even to the extent that these groups of 5 holes, because then there's a gap, line up exactly with each group or each pair of opto-isolators. So yes, it's very beautiful. The question is, will it oscillate? In other words, can you make an isolator oscillator? Well, let's find out. Let's put 5 volts to this thing. So I've got 4 freshly charged, actually they're probably not, Enna loops, about 1.25 volts each, so that's 5 volts. Let's put negative in the blue rail, positive in the red rail. Now, of course, we're going to need feedback. Now I'm going to link the very last stage output via that resistor to the input of the first stage, and now I'm going to switch on. Oh, and it works! Fantastic! And actually that's showing up rather well. I was having problems with this earlier in regard of the camera's sort of scanning rate was interfering with this. Now, I should say this is about 20 Hertz. I'm not sure whether it's coming over as 20 Hertz. It is bang in the middle of the photosensitive epilepsy sort of sensitivity band. So cover one eye and look away now if you have photosensitive epilepsy, but that's oscillating rather well. Now, of course, this is a ring oscillator. We have an odd number of stages here. If you count the opto-isolators, you'll find there are 14, but they're in pairs because these are DCOI circuits. These are my dual complementary opto-isolator inverters. So what I've got here are 7 inverters, and I'm linking the output of the last inverter back to the input of the first one, and yeah, we've got oscillation. These capacitors are slowing the oscillator down. Without them, this runs at something like 35 kilohertz. With them, it's now running at about 20 hertz because each stage is kind of slugged by the capacitor, slowing down its sort of switchover time and giving rise to this. Now, I would like to have done it a bit slower because then it would have been more visible what's going on, because it's not quite obvious what's going on here. But I couldn't find capacitors big enough to slow this down. Now, one of the things that's stopping me using electrolytics, well, the thing that's stopping me doing that is because these capacitors are being sort of charged one way and then charged completely the reverse direction. So I'm having to use non-polarized capacitors here. These are multi-layer ceramics. They're actually 10 microfarads. They're marked 106. Now, for those of you who haven't watched my videos from about 3 years ago, or two years ago maybe, I will draw a circuit diagram of the DCOI element, which is a pair of optos, a pair of LEDs, and I'll also add in the capacitor and the resistor so that you can see what's going on here. I'll do that in a moment. But yes, I'm very pleased that I've managed to get this string of opto-isolators to oscillate, and I'm even more pleased that I can do this. Let me just see if it's going to work. It doesn't always. No, it hasn't. Okay, well, there is a way of kickstarting this circuit. Let me just put positive through this resistor onto one of the stages, and yeah, that kickstarts it into action. Now, you're not seeing this as I'm seeing it. This is actually oscillating at faster than 20 hertz because we've got fewer stages, so the propagation delay through what is now 5 stages is more rapid. It's probably something around 25 hertz, but now what's coming through on the camera is some sort of interference frequency between the scanning rate of the camera and the actual oscillation of this circuit. Right, so the fact that it oscillates as a ring oscillator is good. The fact that it oscillates as a shorter ring oscillator, it is going to need kickstarting. Let's put positive to there. Is extremely good, and I'll explain why. For the 7-stage ring oscillator to actually function, each of the stages needs a gain greater than 1. And in Opto-Isolator terminology, it's called the current transfer ratio, and it's generally given in percentage terms. So we need a current transfer ratio through each of these decoy stages of greater than 100%, and we obviously have it because it's oscillating. The current transfer ratio is the ratio of current going through the infrared LED on the input side to the current that can be made to flow through the collector emitter of the phototransistor on the output side. So yeah, that's obviously greater than 100%, which is very good news. What's even better news, if I connect that to there, oh, it hasn't self-started, so let's kickstart it. I need to go from positive to one of the inputs. Okay, that's kickstarted it. This is even better news, because what's actually happening here, let me get my pencil, is that this stage here, this pair of optos with the green and the red LED, is not only driving back the first stage, so the transistor output is not only having to light up one of these two LEDs, it's also having to light up one of these two LEDs in the last two stages, which are no longer in the loop, but they are sort of on a tail. They probably don't need their capacitors anymore because they're just acting as inverters, propagating the signal further down this line. So it means that we must have a current transfer ratio of, well, either above 200% or certainly getting on for 200%. You may notice actually that that LED there is a fair bit dimmer than that LED there and that LED there. And that's because this stage is having to drive this LED. It's one or the other. You'll see that these are actually alternating. But also this LED here. So this opto transistor is having to drive two LEDs. And for that to work, you need a current transfer ratio approaching or in excess of 200%. Now, these opto-isolators are PC817s. Not sure if we're going to be able to see that. Oh yes, you can just about see it there. PC817s. So let's take a look at the datasheet for the PC817 and see what it says about current transfer ratio. Well, very little. In fact, the only mention of it is on this front page of the datasheet, where it says current transfer ratio CTR is a minimum 50% at IF equals 5 milliamps. Now that's the forward current of the infrared LED on the input side of the opto. So if you're driving that at 5 milliamps, you'll get a minimum current transfer ratio of 50%, but it doesn't say anything. Oh, and also VCE 5 volts, which I'm using 5 volts on my circuit, but it says nothing about the maximum current transfer ratio. However, do you remember these? These turned up in a recent post bag, and these are the NEC, although they're not actually marked NEC, but they're the 2501 4-pin opto-isolator, and the datasheet for these is a little bit more revealing. So on this one, the PS2501, the -1, -2 and -4 are because there are different size packages. You can get 1, 2 or 4 optos in a DIL package. This one actually says the current transfer ratio is a minimum of 80%, typically 300%, but a maximum of 600%, and that's really rather good news. They also say there are CTR ranks. So you've got the K rank, 300% to 600%, L, M. There's all these ranks, including the N rank, which seems like it might just be anywhere from 80, which was the minimum, of course, to 600%, the maximum. I'm not entirely sure what these ranks are. There's also this, which is the long-term CTR degradation. And it shows here that after about 10 to the 3 hours, so that's 1,000 hours, the current transfer ratio starts to drop away. And I assume that's because the light emitting diode, the infrared LED, weakens after a certain number of operating hours. So that also raises the interesting prospect that anything built with these things, after 1,000 hours of use, if you're working very close to the CTR limit, might actually fail. Right, let's draw the circuit diagram of the decoy element, which is the 2 optos and the 2 LEDs and the other bits. For those of you who've not been following the development of decoy from its invention, can't remember, 2 or 3 years ago, there are 2 opto-isolators, like so. Each one, of course, has an LED. It's infrared, so there's the LED, infrared. Now, I actually join these 2 in series, like so, and then I add another LED here, like so, and another LED here, pointing in that direction. Now these LEDs are inside the opto, so we'll put they're infrared, we'll put the little light coming out markers. Oh dear, I've used rather a lot of space. The other thing I wanted to do was mark the red and green. I don't have a red fluorescent pen, only have orange, but let's mark that as the red LED, which is sort of nominally the off state, and I'll mark this one as the green LED. Well, these don't show up very well at all. These were pound shop. Right, on the other side we've got the photo transistor, which doesn't actually have a base, it's NPN, so that's the emitter there. There's another one on this side, also NPN. Now they are linked like so, joined together. So I should write on this that this is DCOI, DCOI, and I'll write out what that means along here. So there it is, dual complementary opto-isolator, and you can see very clearly that there are 2 opto-isolators, and what I mean by complementary is that this is the output. Let's put a little dot there, and we have a pull-up transistor and we have a pull-down transistor. Now on the input side, actually it's the same on the output side, but we have 5 volts here, 0 volts here. That looks like it's going to light all the LEDs up and fry them. It doesn't, because the forward voltage of these 4 LEDs added together, it's sort of, is it about 2-ish volts for green and red, and about 1 point something for infrared? It adds up to more than 5, so these don't light up at all. In actual fact, they do. If I just take this wire off and put it back in, that shouldn't fire up. You might just be able to see a faint glow from some of the LEDs. They do actually emit a tiny bit of light, even with directly across the 5 volts, with nothing pulling this center point, which I'll add in now, either high or low. Now in this configuration, where I'm using this just with decoys driving more decoys, I've also got 5 volts up here and 0 volts down here. This is the output. Let's mark that out. And this is the input. Now the input, you tie either to 5 volts or 0 volts, but of course you've got to do that through a resistor. So let's put the resistor in. In this circuit here, I'm actually using very low value resistors for a reason which I'll come to, 150 ohms, but I'm not going to mark that on here because this can be a range of different values. If I tie this input point, which I'll draw a little circle actually there and a circle there, because those are the input and the output. If I tie that input to 5 volts, I'll actually light up the bottom 2 LEDs. If I tie this input to 0 volts, I provide a current path through the top 2 LEDs, down through the resistor and down to ground, you might call it. And that's why this thing acts as an inverter. This fluorescent orange really doesn't show up on my camera very well, so I'm going to colour that in red, so that we've got red and green. Right, let's take a look at this thing on the oscilloscope. So I'll need to switch that on, it's got lots of whizzy lights, this oscilloscope, this Keysight oscilloscope. It goes through a really nice whizzy pattern of lights. I'm going to have to keep rambling now so that you can see that. Look, it's testing all the lights. Awesome, isn't it? Yeah, let's hook this up to this thing and take a look at the waveforms, the squareness of that waveform, and also the frequency. Right, I'm looking at the output with respect to ground. It hasn't self-started, so I'm going to have to kickstart it. If I can get that between... Right, there it goes. And yeah, we've got a waveform on the scope. Actually, of course, I'm looking at this after that final resistor, so that's not the best place to look at it. Let's look at it at the output of one of the stages. So I'm looking at it actually here at the complementary output, which is being pulled hard to 5 volts and hard to 0 volts. And of course, we've got much more amplitude. And can you see the frequency there? I'll get in a little bit closer. I think you can see here that the frequency is 20 hertz or thereabouts. Now these capacitors, which I didn't draw in the circuit diagram, I really should. If I start taking them out, let's do that, you'll see that the frequency starts going up. It's no longer visible. You've got a little bit of a beat frequency there between the camera's shutter and the unit itself, but that's getting pretty fast now. Oh, and it stopped oscillating. I'm going to have to just kickstart it again, if it will kickstart. Come on. Oh, that's interesting. It's having trouble. I think maybe if I take that last capacitor out, I may be able to kickstart it because it was so asymmetric. Yeah, there it goes. And can you see what's happened on the scope? It's going like the clappers, so let's... wow, yes, that's going pretty fast. Can you see there that it is 9.6 kilohertz? So getting on for 10 kilohertz. Now this capacitor, I tried it in different places, but the best place I could find to actually slow down this circuit was actually the most beautiful and symmetrical and I suppose logical and excellent place right there in the middle. That's where I ended up putting the capacitor to slow this thing down. And you can see that because this is an inverter, if the input is high and the output is low, then this capacitor is sort of charged that way. When they flip round, the capacitor has to flip completely the other way and charge to the opposite polarity. And that's why I couldn't use electrolytics here. I had to use these ceramic caps. They're actually, did I say 10 microfarads, 106? So they're very high value, but they are able to take a polarity reversal. And you can see here just on the top of the waveform, this is a 7-stage ring oscillator. And we're just looking at the output of one stage, of course, but you can just see the little disruptions to VCC, the power supply, where the other stages are flipping states. You can see the other, well, how many would it be? 5, I suppose, inversions. Or is it 6? Oh, I can't work it out. So this to me is hugely exciting. Let's start putting these capacitors back in, see if I can kill this oscillation. Yes, I have killed the oscillation. It doesn't seem to oscillate where I've got one capacitor slugging one unit and all the others are not slowed down. So I'm going to put a few more capacitors in and then try and kickstart this circuit again. Incidentally, the kickstarting has to do with the fact that the decoy has a third state, which is that the input, if you've got these things driving each other in a long chain, if neither of these two transistors is on, then the output is kind of high impedance floating. If that's connected through to the input of the next stage, it's not going to be driving either pair of LEDs. So the input of the next stage is going to be kind of high impedance and floating. So this tri-state, this high impedance state, can actually propagate through a whole array of these things. Right, let's just kickstart one of these cells again. There it goes. Of course, the waveform is much slower now. Much slower. That's running at 36 hertz. Let's see if I can put the remaining capacitors in without killing the oscillation. That's slowed it. 24 Hertz now, and finally down to, I can find the hole, 20 Hertz. Now, can you see where I'm going with this? This oscillator can be thought of as a clock, because it's just a free-running astable oscillator. It's very interesting actually, because it's a ring oscillator. We've got tap points all the way along here, which are at different phases. I've got my second channel on, so yeah, let's bring in the second scope probe and just stick it on one of the other outputs, and you can see that there's a phase. Well, it's quite difficult to interpret because it depends whether this is inverted or non-inverted, but there's definitely a phase angle change. Let's move that to the next one and see how that differs. You can see there that there's a much smaller phase angle change, so this will work as a multi-phase clock. Now, if you can build a clock out of decoys, and you can also build inverters, these are essentially inverters, but you can also build AND gates, NAND gates, OR gates, NOR gates, which I've shown in a previous video. I'll link to that up the top of the screen. Then it does raise the prospect of a decoy, an Opto-Isolator computer. Now, when I first proposed the idea of Opto-Isolator logic, 3 years ago now, this was picked up by Hackaday, and of course there were a number of comments on this article. I'm not sure what the copyright status of this is, so I'm just going to show this first bit on a sort of fair use basis. But within those comments, someone did raise the issue of fan out. And fan out is the number of inputs that one output can drive, and it was suggested that I'd have problems really driving one input from one output at all. But we can see here that that certainly works. And if I move this over to here, I'm going to need to kickstart that. Let's find a resistor. I should put buttons on, which would make this a lot easier. But let's kickstart that. There it goes. You can see from that I'm actually able to drive two inputs. The input of this stage here and the input of this stage here are both being driven from the output of this decoy here. It may not be very happy. The waveform on my scope has gone a decidedly odd shape. But if it's possible to select on test opto-isolators that have a current transfer ratio of 400%, or even, as it was suggesting on the first page of this, I can't find it now, 600% maximum, if we could find opto-isolators with that very high CTR, then we could perhaps drive up to 4, 5, possibly even 6, that would be pushing it a bit, I think, inputs from one output. And because each decoy stage has not just one LED, but two LEDs, if there were such a thing as a decoy computer, it would probably be the world's blinkiest computer. Cheerio.